Welcome to The Explainer. I'm so thrilled you're here with us today. Look, our main goal right off the bat is to completely demystify the multi-layered stock of AI-powered robotics. We're going to build our understanding of a modern robot literally from the ground up. And to do that, we're going to lean on a biological analogy. I mean, think about it. A robot isn't just a clunky piece of metal anymore, right? It actually has a nervous system. It has senses, a brain that learns from experience, and muscles that act on that knowledge. So we're going to explore exactly how all those pieces come together. Okay, let's dive right into this. Here's a quick look at our agenda. We're starting with the AI robotics revolution, then moving into ROS2, which acts as the nervous system. After that, sensing and perceiving, planning, acting, and learning, and then we'll look at how we bridge the sim to real gap before wrapping things up with ethics, safety, and the future. All right, jumping into Section 1, the AI robotics revolution. We are seeing a totally fundamental shift here. You see, the entire landscape of robotics has shifted completely away from those rigid pre-programmed machines we're used to. In the past, traditional robots operated on super strict predefined rules and fixed paths. Honestly, if a part on an assembly line was even a millimeter out of place, the whole robot just failed. But today, by integrating artificial intelligence, modern robots are actually learning from data. They're making intelligent decisions in real time. And this adaptability is exactly why we're seeing robots expand way beyond the factory floor. They're moving into healthcare, agriculture, logistics, and even navigating the totally unstructured environments of our own homes. And what you're seeing here brilliantly illustrates the blueprint of our explainer today. This is the operational loop of an AI-powered robot. It's this continuous, almost biological cycle. First, the robot senses raw data from the world around it. Then it perceives or, analyzes what that data actually means. Next, it plans a sequence of actions and acts by executing those movements. And finally, it learns from that experience to improve its future performance. This continuous loop is the absolute secret to how they adapt to constantly changing conditions. Moving on to Section 2, ROS2, the nervous system. Let's talk about the core software. So to make that whole operational loop actually function, the hardware and software have to talk to each other. And that is exactly where ROS comes in, the robot operating system. Now, despite the name, it's not a traditional operating system like Windows or Mac OS. It's actually this massive open-source software framework of libraries and tools used for building robot applications. It's maintained by a huge open-source community, and it handles the really crucial communication between different robotic parts. Like passing a message from a camera sensor directly to a motorized wheel. The community is constantly updating it too, putting out long-term support releases with these fantastic names like Jazzy Jalisco, which targets Ubuntu 24.04, and the upcoming Lyrical Luth. Now, because ROS2 is totally open source, industry leaders build heavily on top of it. Take NVIDIA Isaac Ross, for example. It's built directly onto that open source ROS2 framework, but it brings massive hardware acceleration directly to the robot's onboard computers, what we call edge AI systems like the NVIDIA Jetson. It utilizes this thing called nitros to unlock some serious GPU hardware acceleration, all while remaining completely compatible with all standard ROS2 nodes. Now, you might be wondering, why does hardware acceleration even matter? Well, the crucial point here is the staggering difference in frames per second, or FPS, when these processes get accelerated. Take a look at the People's SemSegNet node, which is basically what helps the robot recognize people. Standard processing might give you about 566 frames per second, but with acceleration on an RTX 5090, that jumps to a massive 1570 frames per second. That is huge. In the robotics world, processing speed is literally the difference between smoothly avoiding a collision and causing a major accident. High throughput performance is absolutely vital for real-time safety. All right, let's jump to Section 3, sensing and perceiving. Basically, the robot's eyes and ears. Okay, so now that a robot has a nervous system, where is it actually getting its data from? Well, a robot rarely relies on just one single sense. Just like you and I use our sight combined with our inner ear for balance, robots use what's called sensor fusion. This is the process of combining data from a bunch of multiple sensors. We're talking cameras, LiDAR, inertial measurement units or IMUs, and radar. By fusing all these data streams together, the AI creates this highly accurate, really comprehensive understanding of its environment. It's brilliant because it means if a camera gets blinded by a bright glare from the sun, the LiDAR and radar are still there to perfectly map the space. So once all that raw sensory data comes pouring in, algorithms have to process it, right? Isaac ROS Visual SLAM, for instance, allows a robot to localize itself while simultaneously mapping a totally unknown room. We also have packages like NV Blocks that create these incredibly dense 3D scene reconstructions so the robot can foresee obstacles. And then there's Foundation Pose, which tracks objects in full 6D space. It's all built on the backbone of computer vision, which basically allows robots to literally see and interpret everything, from tiny manufacturing defects on an assembly line to actual human facial expressions. Which brings us to Section 4, planning, acting, and learning. How we turn all this data into motion. So the robot can see its environment and it can pass that information along. But now we hit the heavy computation. This is where perception turns into physical, tangible movement. Building this brain involves some seriously complex math, nonlinear optimization, and really deep programming in languages like Python and C++. But, I want to ground this in a more human experience for a second. Bia Adams, who is a student utilizing MIT OpenCourseware to study Python and AI, said something great. She notes, "I find learning to code similar to learning a foreign language, both exhilarating and intimidating." I feel like that perfectly captures the reality of programming these foundation models. We are quite literally teaching machines a brand new language of movement and logic. And at the very core of this learning phase are deep learning and reinforcement learning. Frameworks like PyTorch and its library TorchRL are used to build agents that learn pretty much entirely through trial and error. Using techniques like proximal policy optimization, which essentially acts as a giant mathematical point system, the AI receives a reward for successful actions. It is literally training the robot's brain to maximize those rewards over time, kind of like training a dog with treats. This gets paired with motion planning libraries like QMotion and, increasingly, these agentic vision language models that allow robots to reason about their environment in a remarkably human-like way. So what happens when you put all of that together? Well, the results from recent research are just breathtaking. We're seeing torque-driven reinforcement learning allowing four-legged, quadruped robots to walk, recover from being pushed over, and navigate super rough terrain without even being explicitly programmed with the complex kinematics of how to move their joints. It's wild. And over at MIT, researchers like Andrea Henshaw are using reinforcement learning to train autonomous quadrotors, so drones, to rapidly navigate inside buildings for search and rescue missions. They are learning to navigate unstructured chaos entirely on their own. Let's move to Section 5, Bridging the Sim-to-Real Gap. Time for some safe virtual training. Okay, so here is a really major engineering bottleneck. You can definitely train an AI model through trial and error, but you absolutely cannot afford to let a multi-million-dollar drone or an expensive robotic arm just crash 1,000 times in the real world while it's trying to learn. So the big question that plagues robotics engineers is this. How do we train robots safely before they ever even touch the real world? Like, how do we transition software code into physical hardware without breaking everything in the process? Well, the solution is the digital training ground. Engineers use these hyper-realistic simulators, like NVIDIA Isaac Sim and Isaac Lab, to create a physics-based virtual twin of the real world. By utilizing real-to-sim modeling and backward dynamics extraction, which is essentially just reverse engineering real-world physics right into the simulation, researchers can shrink what's known as the sim-to-real gap. This means the robot can safely experience thousands of lifetimes of trial and error inside the simulation. It learns all those tricky edge case collision avoidance maneuvers for collaborative robots or cobots. That way, when the software is finally deployed onto the physical hardware in the real world, the robot already knows exactly what to do. It's a real game changer. Finally, Section 6, Ethics, Safety, and the Future. Let's talk about the challenges ahead. As this entire multi-layered stack matures, we really have to take an objective look at the hurdles we're facing. The source material outlines some pretty significant societal and technical challenges. From an engineering standpoint, ensuring absolute safety and incredibly reliable collision avoidance when these things are operating near humans is absolutely paramount. Economically speaking, building these systems requires massive development costs and just vast amounts of high-quality data. And then on the societal side, we have to impartially navigate some really complex ethical concerns. We're talking about potential job displacement as automation increases, protecting personal privacy against these advanced visual sensors, mitigating bias in AI foundation models, and answering some really difficult legal questions about accountability. I mean, if an autonomous system makes a flawed decision, who is actually responsible? These are undeniably complex problems, but they are accompanied by absolutely unparalleled technological potential, which leaves us with a final, really important thought to consider today. As these foundation models and human-like reasoning continue to merge with physical autonomous hardware, how will we redefine our collaboration with machines in our everyday lives? We have gone from machines that simply repeat rigid commands to dynamic learning collaborators. It's a massive shift. I really encourage you to keep exploring this incredible world of robotics. Thank you so much for joining me on this explainer, and keep learning.